Hello, my name's Brian Rieder, and the paper I'll be presenting is a comprehensive strategy for contention management in software transactional memory, prepared by several people at the University of Rochester in the Department of Computer Science. So before we get into the paper, I just want to present the abstract at a high level. The idea of this paper was to address contention management, and that refers to the mechanisms that are basically used to ensure that everything keeps moving in a system. Namely, they want to avoid live lock and starvation and continue to promote throughput and fairness. Now, a lot of the previous approaches before this one were designed for obstruction-free frameworks, so basically the code was thought to be relatively independent, so there wouldn't be a lot of conflicts. And the presence of those obstructions, if they came about, imposed significant constant time overheads, which meant that every single time there was a conflict, there was an issue that had to be resolved. Priority-based approaches required that these reads be visible to all transactions, so basically that generated a lot of computational waste. So the strategy that they're proposing depends on three things: the lazy acquisition of ownership, extendable timestamps, and an efficient way to capture both priority and conflicts, which we'll go through piece by piece as we go through the paper. They introduce two mechanisms for doing so, one of which utilizes Bloom filters and the other using visible read bits. But the main idea is that they're unifying the notions of conflict resolution, inevitability, and transactional retry. To give a little bit of background, because I know not everybody knows what software transactional memory is, I know I didn't prior to this paper, it's effectively just an alternative to lock-based synchronization. What we basically learned with mutual exclusion is that you give a lockout to access a resource in a critical section. However, this basically takes an approach similar to that of database transactions. Now, some people might be familiar with the ACID properties of database transactions. This really just uses the A and the I, which we'll get into in a little bit. Now, because of this is implemented in software, so all of the management of who has the lock per se is done at a higher level. This means the transaction occurs when a piece of code executes a series of read writes to shared memory, and the goal is to make them logically occur at a single instance in time. That's the atomicity part that would be part of ACID. The intermediate states, consequently, should not be visible to other transactions occurring in the system, so everything appears as if it happened at once. A good example of this would be the insertion of a node into a doubly linked list. So you insert the node, you put its previous pointer to point to it, and its next pointer to point to the next node. However, if somebody were to read that in the middle and see that it pointed to null instead of pointing to where it actually was supposed to be pointing, the atomicity of the transaction would be violated, and therefore it wouldn't actually look correct, and you'd have malfunction in your code. So a good example of how this could be done wrong is shown below. So if atomicity isn't satisfied, we can see on the right side that x and y should increment at the same all the time. If we assume that they started at the same value, that would mean that x and y would always be equivalent. However, if this is ever violated even for an instant, the code on the left side would then enter an infinite loop and the code would break. So the paper itself references two things quite a bit. Algorithms here typically achieve atomicity in isolation, the A and I in ACID, either at encounter time, which is eager acquire, and commit time, which is lazy acquire. Up to this point, most of the work is resolved around conflict resolution, which chooses when transactions conflict, which will continue and which will later abort. You'll see that most of the work so far has been done with eager acquire. However, the authors of this paper push for lazy acquisition. So just to go through some of these in a nutshell, here's some of the popular current policies for conflict resolution. So the first one is the one that we'll reference the most. It's passive. So in passive conflict resolution, transactions self-abort if they detect a conflict with concurrent writer. So if you have a regular access pattern, or basically single-threaded operation, if it's consistent, you'll basically have relatively low latency on your transactions, because the assumption here is that a consistent access pattern won't cause conflicts. So, but if there is one, will automatically abort. Next is polite. This is basically the original. This is something that the authors have borrowed from. So in this case, if a transaction discovers that a conflict exists, it defers to its competitor using randomized exponential backoff. Now, if they were to use this backoff, so they're there waiting and waiting, if they exceed a certain number of times, they abort their competitor. This basically allows conflicts to resolve themselves without aborts. It's kind of running out the clock. Not necessarily the most robust, as it can cause things like starvation and live lock, but is a solution nonetheless. Next is karma, another thing that the authors borrow from. So in essence here, the idea is that the more time you spent on a transaction, the more work you've invested, which means you're less wanting to give it up. So that means that if you've been working a long time on a single thing, you're going to avoid aborting it as much as you can. So what it does here is it tracks the number of transactional objects accessed by each in-flight transaction and gives priority to the one with the larger count. Sort of a maturity kind of aspect of this that we'll get into a little later. And the last one is greedy, another thing that the authors borrow from. And in this case, using visible reads, which is basically similar to the read-write locks that we would be familiar with from mutex, and favoring based on start time, we're able to avoid both live lock and starvation. Now this comes at the cost of high latency on every single read, since there's a lot of overhead associated with checking all of this, even in contention-free workloads. However, there proves to be some merit out of that. Now, the authors of this paper weren't particularly satisfied with any of the previous approaches because none of them satisfied both the goals of low overhead for low contention workloads and good throughput and fairness under high contention. They all seem to specialize in either low contention or high contention, and the authors wanted to sort of address that. Now, they claim to do so and to support user-defined priorities, which is something that they felt was necessary for people to have a functional solution, by providing their two candidate implementations of Bloom filters and visible read bits. The main idea here is they want to address conflict resolution by forcing lower priority transactions to defer to higher priority transactions, but only in the presence of an actual conflict. There shouldn't be any yielding whenever there doesn't need to be. Now, getting into a little bit of their thought process here, timestamps and wasted work were a big point of contention in the past and why lazy STM was sort of dismissed. So, intuitively, lazy STM is shown to scale worse than eager STM due to wasted work. A good example is below, where you see that A reads from L and B reads from L. However, later on, A finally commits. Now, all of that time that B has been working with the data from L prior to that commit and after its read is effectively wasted. So, if we suppose that transaction A writes location L and then concurrent transaction B reads L before A reaches its commit point, if A commits, all instructions issued by B after its access to L constitute wasted work. What's often not recognized here, though, is that in a system with any significant number of conflicts, there's a good chance that if B aborts eagerly when it discovers its conflict with A, all the work that's done so far will be wasted if A subsequently fails to commit. Conversely, if B forces A to abort, then all of A's work will have been wasted if B ultimately aborts. So the consideration here is that you won't necessarily be successful, and we need to consider that. Now, in the past, whenever they've done evaluations between lazy and eager acquisition, historically TL2, or the passive approach as shown a few slides ago, has been used as the representative for lazy STM. Now in TL2, a transaction T samples the current time from a global clock, and if it ever encounters a location where the most recent update occurred after that time, it aborts and restarts. So that means that any time it notices a conflict, it will automatically abort. Now these TL2 style timestamps result in low latency, but they're inherently pessimistic and reduce scalability by aborting on some pretty easily resolvable conflicts. The counter proposal here is the usage of extendable timestamps rather than simple timestamps. So in extendable timestamps, T resamples a global clock as C prime and then checks that all of the past reads remain valid. If any check fails, this transaction will abort. Otherwise, the transaction's execution is equivalent to the work performed up to that time, so it sets its clock to that value and continues. Now, extendable timestamp implementations may require a handful of additional instructions on every read, and thus have lower single-thread performance than something like TL2. But in multi-threaded execution, a transaction with extendable timestamps may be forced to validate on each read, but in TL2, that same transaction would abort and restart that many times. That basically means that we're able to go back and check if we're valid still, rather than just giving up on it immediately, which in a high conflict system causes a significant amount of heartburn. Now regarding preventing aborts, TL2 and TinySTM advocate passive contention management strategies. That is, they abort when they encounter a lock. So revising this strategy we come up with something called a patient strategy, meaning it's willing to wait its turn. Now, this uses a combination of extendable timestamps as lazy acquire, as we sort of alluded to previously. And the strategy here basically boils down to when we encounter a lock, we simply wait. We don't automatically abort. If this lock is the first instance of the conflict between those two transactions, the waiting transaction just revalidates and continues once the lock holder commits. When that transaction reaches its commit point, it only aborts if it can't acquire all locks. Now, while that transaction is waiting, it yields the CPU if there are more active threads than cores. Since this waiting transaction is invisible, its wait can't block any other concurrent transactions. Moreover, aborting the lock holder here wouldn't make much sense either. The lock holder would have to release the lock before the waiting transaction could proceed, and since the lock holder is already in its commit protocol and probably about to finish up, aborting it is really not likely to make it release the lock much sooner, so it really makes sense to just wait a bit. Now, the first of the two implementations is priority read bits. So this adapts the visible reader bits employed in RTSM that we talked about earlier and maintains two things. The first one is an active transaction table in ATT that contains T entries. Each of those entries corresponds to an active transition with some non-zero priority, and it also maintains L leader records and uses a hash function to map those addresses to RRECs, or leader records. Now each RREC is a T-bit array where each bit corresponds to an entry in the ATT. So the API that they effectively present here has a couple main functions, the first of which is request prio, or for requesting priority. Now this succeeds only if a transaction can identify an unreserved element I in the transaction table. If it's able to, it locates the RREC corresponding to the input address and sets the ith bit of that RREC. It also keeps track of this so that it's able to reset that bit after it's done with its commit or if it's aborted. If it can't find an unreserved element in the ATT, it still records its priority in the hope that it can run execution without protecting its reads without RREC updates. Now, if it can't, it will attempt to reserve an ATT entry each time it restarts until either it reserves an entry or it commits. Now, when a transaction is ready to commit, prior to committing, it calls the function precommit. Now, this function takes as a parameter the write sets whose corresponding locks were just acquired, so basically everywhere we want to write to, and builds a summary RREC, which is a union of all of those corresponding RRECs. After that summary is built, each bit is tested, and if any bit I is non-zero and the ith element of the ATT represents a transaction with a higher priority than the caller aborts and effectively yields. Now, aborting lets the caller defer to the higher priority transaction, and upon abort, the karma, as I mentioned earlier, associated with the transaction is incremented, which is a value that's represented in the maturity of the request, which is basically the strategy that they employ here to avoid starvation. This approach has three significant advantages over the traditional way of doing things. The use of a global table of RRECs avoids any need for dynamic memory allocation. It's purely static. The RRECs covering multiple locations can be unioned to create a complete list of potentially conflicting transactions with no duplicate entries. And for large values of T, that is the number of entries in the transaction table, SIMD instructions, or single instruction multiple data, which is basically the same operation on multiple data points simultaneously, those instructions can be used to accelerate the creation of the summary RREC. It's worth noting that the creation of the summary RREC is the most significant overhead of the entire process, taking O of WT time, where W is the number of writes and T is the number of entries in the table. Now, the second approach that the paper presented was utilizing Bloom filters, or effectively priority read filters. Now, unlike priority read bits that we showed previously, this mechanism has no memory footprint, so it's purely dynamically allocated. And it maintains a list of transactions with non-zero priority, where each list entry contains a reference to the corresponding transaction and a Bloom filter representing the addresses passed by that transaction to the function that marks priority. Now, I know I didn't know what a Bloom filter was walking into this, so for background, it's effectively just a data structure that is designed to tell you whether or not, in a rapid and efficient manner, an element is present in a set. Now, the price of this efficiency is that a Bloom filter is a probabilistic data structure, so it can't tell us anything definitively about whether or not something is in the set, but rather if it definitely is not, or maybe in the set. Now, that same request prio function from earlier that requests the priority is far simpler. It actually just appends an entry to the list of requests. And at commit time, transactions scan through this global list for entries corresponding to any higher priority transactions. So for each entry, the transaction must check if any address in its write set is stored in the filter. Now, a filter configuration using a single hash function can make this heavily optimizable. They do recommend using multiple, but there is potential here. And then the pre-commit function that is called write before commit constructs a filter representing the caller's entire write set. It takes this filter and intersects it with a filter corresponding to any other higher priority active transactions. And if the result is non-zero, the calling transaction aborts. To summarize a few things that came out of this presentation, these implementations allowed the authors to unify priority, retry-based coordination, synchronization, and inevitability using only a single mechanism. It stands in contrast to the early work on contention management by focusing on lazy acquisition rather than eager acquisition in a highly optimized runtime, and argued that extendable timestamps actually made lazy acquisition, which was previously somewhat dismissed, competitive with eager acquisition for well-behaved applications. And more importantly, in poorly behaved applications, the narrow commit window of lazy acquire allowed it to dramatically outperform eager acquire. So this effectively eliminated LiveLock as a practical concern by the introduction of these extendable timestamps, but also because we weren't throwing out as much work. So in a high contention environment, we're running into the issue where an eager acquisition method would constantly be throwing away work that wasn't necessarily wasted. So in this regard, lazy acquisition allowed it to perform much better. And they went over an extremely simple patient policy for contention management that allowed them to minimize these unnecessary aborts by just simply waiting instead of throwing away things incessantly. So the two questions associated with this presentation are, in well-behaved applications, why was it argued that lazy STM scaled worse than eager STM? And what was the mechanism that was employed to counteract this downside, and why did it improve performance? And in poorly behaved applications, why does lazy acquisition of STM outperform eager acquisition? Thank you.